We also have another theorem that we can use to prove that two triangles are congruent, and that is called the angle-angled side, or AAS Congruence Theorem for short. So this one says if two angles in a non-included side of one triangle are congruent to two angles in the corresponding non-included side of a second triangle, then the two triangles are congruent. So I see here I again have two congruent angles, but instead of the included side being congruent, like we saw last time, we instead have the non-included side. So now it's a side off onto the other side of these two angles. And whenever we have that, that means that these two triangles will be congruent. So here we'll see that triangle ABC is congruent to triangle DEF. So now let's go through some proofs. So here I have that HF is parallel to GK, and I also know that angle F and angle K are right angles. So that's the information I'm given. And then I want to get to prove that these two triangles are congruent. So angle HFG is congruent to triangle GKH. So first, I know that when I have angles that are both right angles, that means that they're both congruent. And I know that by the right angle congruence theorem. So I already have an angle that is congruent. I am also given that these two sides are parallel. And so again, that means that my alternate interior angles will be congruent. And so it doesn't matter which one you decide to do. I'm going to go ahead and do these two angles. You could have also done these two for the same reason, but I'm just going to go ahead and use these two. And so I know, since these lines are parallel, that angle FHG is congruent to angle KGH. And that's because they're alternate interior angles. And again, that is because these lines are parallel. And so that gives me another angle that's congruent. Now I just need a side. Well, I noticed that these two triangles both share a side. They both share the side HG. And I know by the reflexive theorem that HG is congruent to HG. It's congruent to itself. So I have an angle, I have a side, and I see that this side is the non-included side, because my angle right here is my right angle, and then this side, which is non-included. So that means that these two triangles are congruent by angle side. Okay, let's look at one more. Here I'm given that AD is parallel to EC, and BD is parallel to, or congruent to BC. So this is the exact same proof that we saw in the previous video, but I just want to show you another way that you can prove this using angle side. And so again, we already have the side that is congruent. So now I want to get those two angles. Well, both of these lines right here actually act as transversals to my parallel lines. And so that means using alternate interior angles theorem, angle D is congruent to angle E, and angle A is also congruent to angle E. Or we'll go ahead and use the three letters. So I have that angle ADB is congruent to angle ECB. And I know that angle DAB is congruent to angle CEB. And again, that's because they're parallel lines cut by a transversal, and those are my alternate interior angles. So both of these reasons are going to be alternate interior angles theorem. And so that gives me my two angles that are congruent. And so I can therefore say that these two triangles are congruent. And that's going to be by angle, angle, side. So my angle, I have an angle, and then my side is not included.